Trillions of years from now, the final star in the universe will die. It will not collapse into a black hole or explode in a brilliant supernova. It will simply fade into complete darkness. That moment is barely the end of Chapter 1. The cosmos continues long after the last light dies, entering into deeply strange eras defined by cold remnants, empty space, and dissolving matter. The object that will mark the end of the starlit era is a red dwarf. It is the smallest, dimmest, and least massive class of star that can physically sustain nuclear fusion. Mapping the life cycle of these tiny stars is the only reliable way to understand the mathematical limits of the universe. Because they are the ultimate cosmic survivors, their timeline is the universe's timeline. Our universe is roughly 13.8 billion years old. That sounds ancient, but the peak era of star formation, when the cosmos was churning out new stars at its maximum rate, already ended about 10 billion years ago. We look at our sun and assume large, brilliantly glowing stars are the standard. In reality, our sun is an outlier. At least 70% of all stars in the universe are red dwarfs. This image of the southern sky highlights Proxima Centauri, our closest stellar neighbor. It sits just over 4 light-years away and is a classic red dwarf, yet it emits so little light that it is entirely invisible to the naked eye. In fact, 50 of the 60 closest stars to Earth are completely hidden from us for exactly the same reason. The bright giants we trace into constellations are rare exceptions. The true main characters of the Milky Way are these hidden, low-wattage runts. A typical main sequence star like our Sun will fuse hydrogen for about 10 billion years before expiring. A red dwarf, burning fuel at a fraction of the rate, can easily continue shining for up to 10 trillion years. This animated diagram compares the interiors of these two stars. In a standard star, nuclear fusion happens exclusively in a highly pressurized core. Over time, that core chokes on its own byproduct, a dense helium ash, which eventually halts the fusion process while leaving a massive outer layer of unburned hydrogen floating uselessly above it. A red dwarf operates on a different mechanical principle called convection. The internal gases are in a constant state of motion, with hot fluids rising to the surface and cooler fluids sinking back down. Looking at this timeline, you can see the result. Because of this continuous mixing loop, the helium byproduct never accumulates in the center. The star pulls fresh hydrogen from its outer layers directly into the fusion engine. It stretches a tiny fuel reserve over trillions of years because it consumes literally every available drop. In the physics of stellar evolution, raw size is a disadvantage. A small, efficient engine that recycles its fuel easily outlasts a massive one that suffocates on its own waste. Their extreme longevity makes red dwarfs a compelling target for astrobiologists. If life needs billions of years to evolve and adapt, a star that burns for trillions of years provides the longest possible runway. But the habitable zone, the orbital region where temperatures allow for liquid water, sits incredibly close to a red dwarf. Orbiting that tightly introduces a severe mechanical hazard called tidal locking, where the star's gravitational pull forces the planet's rotation to perfectly match its orbit. One hemisphere of the planet faces the star, resulting in a scorched, blinding day. The other hemisphere is trapped in a frozen, eternal night. The atmosphere also has to survive the star itself. Red dwarfs frequently emit violent bursts of high-energy radiation, known as stellar flares. These volatile magnetic eruptions can strip away a planet's atmosphere before biology even takes hold. Any biology that manages to survive in deep oceans or narrow twilight zones faces a brutal environment. Yet, with a lifespan stretching into the trillions of years, the sheer volume of available time makes these chaotic planetary systems the most mathematically probable final oasis for life. Skip forward several trillion years. Even the most efficient red dwarf will eventually fuse its last available hydrogen atom into helium. This data visualization plots what happens next. While a standard star would expand into a red giant, a low-mass red dwarf has a highly transparent atmosphere. To radiate its remaining energy, it simply increases its surface temperature. As the plotline shows, it grows hotter, shifting its color spectrum to become a theoretical object known as a blue dwarf.
The blue dwarf stage is the final gasp of active fusion. Once it burns out, the engine stops. The era of shining stars comes to a close. What follows is the Degenerate Era. The cosmos is populated by the cooling corpses of stars, white dwarfs, neutron stars, and the black holes that swallow them. As time stretches into numbers too large to name, physics predicts a process called proton decay. The protons that make up the atoms of these dead stars will slowly lose stability and dissolve into lighter subatomic particles. This photograph shows the Super-Kamiokande detector, buried deep under a mountain in Japan. Physicists use vast, ultra-sensitive tanks of pure water like this one to watch for the exact moment a proton decays, trying to prove that matter itself has an expiration date. Once the last black holes evaporate and the final protons dissolve, the universe reaches thermodynamic equilibrium, or heat death. The temperature approaches absolute zero, distributing energy so uniformly that no further mechanical work can ever occur. The cosmos becomes an endless, completely inert sea of drifting particles. The math predicts a long, quiet, and inevitable end. We happen to exist in the brief early window where stars ignite, galaxies collide, and planets form. The light we see when we look up is a temporary condition, making our vantage point a fleeting anomaly in an otherwise dark eternity.